pleased to introduce Jayesh Patel. Jayesh Patel from Rockstar Games will be presenting on modeling large volume of data using Spark and will uncover how to enrich data on big data platform. He will be presenting a talk titled Big Data Modeling with Spark SQL, Make Data Valuable. Please join me in welcoming Jayesh.
Thank you, guys. Welcome to the session, Big Data Modeling with Apache Spark SQL, and we'll uncover how to make data valuable using big data tools. Let me introduce myself with some of the brief detail. My name is Jayesh, as my friend introduced. I'm currently working for Rockstar Games as a senior data engineer, and I have been working in the data analytics space for the last 14 years, building data-driven processes for various industries, not limited to pharmaceuticals, telecommunications, gaming, marketing services, and public transportations. Other than that, my expertise is in developing end-to-end solutions for big data pipeline, machine learning models, and data models. I'm also a senior IEEE member and a contributor. So today, here's the outline of today's session. I'll be providing brief on the data modeling, some of the challenges with traditional data models, and why we need to think differently for big data models. Then I'll provide a summary about Apache Spark and Spark SQL. Then we'll go over data modeling with big data, some of the concepts and principles on how we can effectively model big data. At the end, if time permits, I'll cover the case study. And I really want to show a demo on Spark SQL, how you can process data using Spark SQL. At the end, I'll spare some time for Q&A as well. So let's start with the data modeling. You may know about different concepts in our life. For example, when you go to library and you want to find a book, it's easy to find because they have a system in place that kept all the books organized in the library. Similarly, when you have massive amount of data in your big data platform, there is a need to manage, store, and organize the data in that platform so that whenever stakeholders want something, whenever they need some information or data to make decisions, it has to be organized. And the method that we call to organize and store data in our platform is data modeling. There have been multiple data model technologies and scenarios that we have been learning since last several decades. There are mainly two kinds of applications that we see in our day-to-day business cases. First one is OLTP, Online Transaction Processing Systems. And the main purpose of this application is to track real-time transaction processing and store it so that business people can see how transactions are moving. And they are mainly to support insert, update, and deletion of different operations. It uses the relational models on the back end to store large volume of transactional data. The second application type is OLAP, Online Application Analytical Processing. The main purpose of OLAP applications is to analyze large amount of data. And for that, we use different kind of techniques to store data. And dimensional modeling is one of the popular methods. That's how we model data for this kind of applications. Entity relationship models is one of the popular one as well, and dimensional modeling for data warehousing and OLAP applications. One of the differences between OLTP and OLAP, like when we think about data modeling, for OLTP, the main operation is random read and write. But for OLAP, it's batch read and write. That's one of the distinct operations that we have to think when we model in these applications. Some of the challenges that we face when the data scale, when the data volume grows. Some of you might have tried to bump up SQL Server Data Warehouse or Oracle or some of the traditional RDBMS, and you might have faced these challenges. The first challenge is it is too expensive to scale out any RDBMS. Like when you have cluster of SQL Server or Oracle or some of the other RDBMS, and to handle the data growth, when you add more servers in your clusters, you'll hit by several other costs. That scaling cost will be too high when you try to do that with those RDBMS applications. The second is too much machine time. When you add more servers and when you run complex analysis on those models, it will take so much time. The response times will grow bigger and bigger every time you add more data and more servers in your RDBMS cluster. And the last one is it can't handle data variety. If you remember, for your data warehouse, when you start designing it, the first question you ask is, what's the business processes that you want to handle with this data model? What are some of the key questions that will be answered by this model? So those preset of questions will define the data model. If someone asks different questions than those preset, you will need either different data model or different kind of structure to handle those kind of varieties. There are several more, but these three are the key challenges to scale out RDBMS. Now to move on to describe big data, there are 5 V characteristics of big data. Someone describes it as 7 V, someone says 3 V, but I will go with 5 V and we'll go over like what are those characteristics of big data. The first one is volume. That's why it got the name big data. The data volume, if you look at big data as a pyramid, it sits at the very bottom because that's the base of big data. It has to handle large volume of data if there is a big data platform. The second is velocity. We have different sources of applications, different sources of data in our enterprises. Some applications generate data at a high velocity and someone at a slower speed. To ingest that data, a platform should be able to handle the different kinds of velocity. The third one is variety, different forms and different types of data. As we use different types of applications, it may generate different kinds of data, structured data, semi-structured data, and unstructured data. To deal with them when we think of big data. The next one is veracity, uncertainty of data. When you have massive amount of data, one question will always strike. Are we missing something? Is this data accurate? Is it consistent with what we have known so far? So that's veracity. And last one is value. That sits on top of the big data pyramid. And the value means the ability to transform this tsunami of data into a business. So these are some of the key components of big data. Now we know like what is big data. So let's compare our traditional data modeling with big data. The first key difference between those two is how we design it, how we approach, how we process it. For traditional data model, first we design. First we design the data model and then we build it. But for big data, the process is different. First we discover that what we have, what we can do, and based on that analysis, we perform our task. There are a few other differences, and this diagram shows that. The usage of the data in traditional and big data modeling. Traditional data model, it uses like slicing and dicing, hierarchical analysis. Most of the times you will see that when someone looks at the high level number, like say year over year growth was 20%, then the next questions will be that 20% year over year growth, which department had the highest? Why? What are some of the key considerations for that growth? Those questions will be answered by that hierarchical and top-down approach. But with big data, the data usage is distributed. Someone might want to look at the explorative analysis, and someone might want to consider how we can utilize this data for marketing and customer service. So the usage is democratic. Traditional data model look for the push or passive structures, but big data, it is more collaborative and iterative. As we have more and more data coming, collaboration is very important in big data. The data volume and the amount of information that we store in traditional data model, it's manageable, and the growth is still at a steady pace. With big data, there's massive volume, and the growth is exponential. And one of the main purpose of traditional data model is business intelligence. For big data, it's mainly used for statistical analysis, machine learning, and AI. These are the key differences between traditional and big data models. Now, as some of you might be already using big data platforms, and some of you might have already built data models, what happens after that? What happens after you build one, second, third, fourth model? After few months and few days, you will see so many data models, and these challenges will arise. That there are too many data models. Which one that I should use? One model shows different number than the other model for the same metric. Why is that? Some of the model stop refreshing after certain date. Some of the model, when I join in my query, like multiple fact tables, as the data volume grows, if I want to do live to date analysis, joining two large fact tables will create big joins, and the query will run forever. These are some of the challenges that we run into when we model this big data and we have a bunch of big data models. So what to expect when you have created this many data models? Now you want to revisit that process, that how you can better model this data and create effective and scalable data models. What to expect while doing that? The first thing is performance. The query should be faster and the I/O throughput should be reduced. The second is cost. One of the things that we usually misunderstand is the storage is cheap on big data. We have too much processing power on this distributed platform. But that doesn't mean that we should just create more and more models. We should still think about reusability. We should still think to not duplicate the data in our data model. When we do that, it will reduce the cost significantly if we reuse our insights. The next one is efficiency. If you think about data utilization, like out of, say, you have 100 terabytes of data, data utilization may be 1 or 2% on daily basis. Think of that efficiency rate, that how you can bump that up, how you can leverage the data utilization by building better data models. And the last one is quality. The consistent metrics, if you deliver it, it will reduce the cost eventually, because there will not be any questions about why the numbers are different, why there are some computational errors. If we have quality data models, these questions will not arise. Now let's move on to an open source technology named Apache Spark. It's an open source processing engine that provides bunch of different tools, bunch of different APIs that can handle structured, semi-structured, and unstructured data. It provides a unified analytics engine to perform our big data modeling, big data integration, and machine learning. It has the largest open source community. It was founded at UC Berkeley's AMP in 2009. Then it was open source in 2010. It was donated to Apache Software Foundation in 2013, and by February 2014, it became the largest Apache project. It supports a variety of different sources. These are some of the known ones, but there are several others that we can't even put it in one single diagram. Apache Spark, the core of Spark, the fundamental component, fundamental data structure of Spark is RDD, resilient distributed data sets. Because of that, Spark offers parallel and distributed computations and transformations. One of the other features of Spark is fault tolerant. All Spark jobs are fault tolerant. Since RDDs are resilient and immutable collections of data, collections of objects, it remembers the lineage of operations. So when something fails, it exactly knows what operations had been carried out on that data set. And as it is immutable, it can revert back in case of failures. That's why Spark is fault tolerant. And it has different benefits because of being fault tolerant. The last one, and pretty important, it evaluates lazily. What does that mean? When you create a data frame or data set from your source data, it will create an RDD behind the scene. You apply different transformations. You do union, you will do map, you will do join, all sort of those operations, those are transformations. It will create other RDDs, data frames. When you perform those operations, it will not do any action. It will not create any results at that point. When you hit an action, it will generate the result. It will evaluate all different transformations that you specified so far at that point when you specify the actions. Reduce, show, first, count, those are actions. And as it evaluates lazily, it offers bunch of performance benefits. Spark SQL, initially it started with Hive, then Hive got integrated in Spark, and that's how Spark SQL was born. It offers relational processing with Spark's functional programming. And it's very important, when you integrate both of them, it will be really powerful when you process your data, because you can query your data at the same time, and you can do the functional programming on top of that data in distributed and parallel processing. In this diagram, you can see you can use a bunch of different applications, user programs, JDBC, or console to use Spark SQL. Spark SQL also offers data frame API, and that offers all those relational operations and transformations in that API that you can perform on data frame. It also has Catalyst Optimizer. That's one of the important pieces as well. It supports HiveQL, SQL formats. So if you know SQL, it's easy to use Spark SQL. It offers all standard aggregation, window functions, and other features of SQL. So this is like to give you an example that how you can use Spark SQL. This is one of the query that we have. As we all might be knowing SQL, it will be easier to interpret this, that we can use this query and get the result back. But at the same time, it offers the similar functionality that you can apply on data frame. And here is an example. Both will return the same results at the end. It will do the same functions. Performance is the same for both, and you will get the same results by doing both of these approach. Now, when you have started big data modeling or building models in your big data platform, you might have used Hive. And I think most of the big data project, when it starts, people start querying. They will apply business rules, and that's how the data model is born. And it's easier to create data models in Hive. But when Spark born, there are a bunch of different benchmark analyses that Databricks, Facebook, Yahoo, everyone performed, and they provided all those results, that how faster Spark is when compared with Hive. I'll not go in much detail, but these are some of the performances that Facebook has published in 2014 when they implemented Spark with one of their complex data model with 60 terabyte plus scale in production. It was in 2014. Now, after 5 years, it is much more capable and can do more larger things. It offers like bunch of benefits in terms of performance, CPU time, and query response as well. Now, let's discuss some of the principles of big data models. As we are thinking of big data, that doesn't mean that we can't leverage some of the things, some of the good things that we have been using so far. Dimension model is one of the example. We can still think dimensionally when we are designing data models, because that's very easy for business users to think about data in terms of dimensions and facts. So when you talk to them, it's easy to have that conversation with them because they know about those concepts. When you are modeling, always use confirmed dimensions. Some of you might ask that question, that what is that confirmed dimension and why should I use it? Confirmed dimension is a glue that sticks together variety of data sources. And when you want to do the analysis, all those variety of data sources can be combined to do a single analysis. That's the power of confirmed dimensions. And that's one of the key feature or key learning that we have inherited from traditional data model or dimensional models. And that's one of the favorite piece of Ralph Kimball, the inventor of dimensional models. When you model big data, expect that you'll be dealing with structure, semi-structured, and unstructured data. There will not be always the case that you'll be typing a query and you'll get the results back. You might have to deal with semi-structured and unstructured data that you have to process before you store it into a structured format. Divide and conquer. Even though you are using distributed processing, the process will take hours to run. The process might take days to complete their tasks. You have to think that at which point you can divide that job and make the processing better. Divide and conquer doesn't go away in big data platform. When you join large fact tables in big data environment, it will cause more damage than getting you results back. So you should always think about a modeling technique that can avoid joining of large fact tables. Now, how to do this? These are some of the guidelines that we learn, but how to do this when you start modeling? Think that one grain, like you think of dimensions that you want to analyze something by customer, by day. Once you define that grain, put all those metrics in that same model, regardless of the business process. Even though you are marketing, customer service, security, all other departments, if the metrics fall in that grain, put in a single model. I will give you the reason why to do that later. The next one is denormalize. With OLAP, online analytical processing, everyone says that we need to denormalize in order to better utilize our models. With big data, it is true as well. And it's true in that level that you don't need to even follow the star schema. Put those attributes in the fact table itself to make the table bigger and bigger. The reason is the block size in Hadoop. The default block size in Hadoop is 64 MB to 128 MB, and it may be even higher for some cases. But RDBMS, like relational databases, the default block size is less than 32 kilobytes. So the blocks that you're reading, it's pretty small in relational database systems. In Hadoop, it's pretty big. So even if the record is pretty wide, you can still read in one block. 128 megabytes, it's pretty large information. It can contain so many information. Even though you have like multiple metrics in one table, it can still handle that. So denormalize whenever it is possible. Batch model, that's where we have to think about divide and conquer. If we can't handle the volume of daily transaction, break it down. Run it every hour, every few minutes, or even in micro batches in terms of seconds. Spark offers that. Transitional models. Sometimes when you try to integrate multiple data sources, some of the sources generate data at higher velocity. And there are so many transitional data that might be harder to integrate at the same time. Transitional model will relieve that pain. If you model that data in such a way that data model at the later stage can efficiently use that will speed up the data modeling process. And that will also avoid the large table scans. And the last one is data model lineage. We never think of like when we build data models. When we build data models on top of those data models, when other people build data models on top of other data models, it creates the lineage of data models. When something fails, it becomes a nightmare. That which model that I should reprocess, which model that I have to refactor in so that everyone get the accurate information. So better to maintain that lineage of data models, even in big data platform. I think we still have some time. I'll go over the case study in brief, and then we'll jump on to the demo. I'll provide a case study of a healthcare provider. I worked on a platform that provided software as a service solution for more than 80,000 medical providers in North America and serving over 100 million patients in North America. So this platform provided electronic health records, practice management, and revenue cycle management solutions for healthcare providers. And there were multiple sources of information, like for each provider, for each practices, they are maintaining a single database. And when you perform the data modeling, you have to think about how you will get the information of thousands of databases, how will you integrate it, and how will you build a model. I was using Apache Spark, Python, and Kudu to build this specific model. And these were some of the metrics that I had to provide analytics on. These are just the top 3. There are several others. But when you think of the traditional data warehouse, you will see these 3 as a separate data models when you analyze it, because they are from different functional group or different processes. So claim facts involves like number of claims, how many claims were denied, rejected, and several other stats on claim facts. Payment fact shows how much balance is left on patient and insurance, how much AR the revenue is outstanding, and at the end, patient fact, number of patients per day, how many patients that the provider is provider is providing care, number of repeat patients, number of new patients, all these analytics, and there are several others as well. So how did I do that? So I had to think of integrating all those sources first, clean it up, and then utilize that data. So first step was to get the source data in a single platform. I was using Cloudera's Hadoop platform. So set up those processes in SQL, got the data on in flat files, ingested on that platform to load it into our staging tables, and from there, after cleaning, using it for analytics. So each source involved multiple tables. So the first task was to integrate. Some of them were having semi-structured JSONs. Some of them were having structured data. So processing and keeping that data ready at the stage where the modeling process can utilize that. And same thing with other sources. At the end, once the sources are ready, pulling data one by one, or you can join all 3 at the same time and load into a Kudu table. Kudu handles iterative processing. So even though you want to only refresh one metric, you can still do that. Use Spark as a processing engine and storage as Kudu, you can do that. At the end, you can get a provider analytics table, and that you can leverage more on. That fact table was pretty big because it had a bunch of other metrics. After a couple of months of having that model ready, the thing is, people started asking for more and more metrics. It was way easier to maintain this table than having something in traditional data model or traditional data warehouse. Because as Kudu is absurd storage, you can add a metric at the end and add that metric in your processes, and it will just take care of that. But you have to make sure that the source data is there. If it is there, you can scale this model up and up whenever new request comes in. So that was the provider analytics fact that I have worked on. Now, I'll briefly present the results, like what happened. Initially, it started with the nightly process. Let's get everything on nightly basis. The later, what happened was they wanted some information pretty fast. So we scheduled some processes every few minutes. When the data is ready, it will update the Kudu table only for high priority metrics. And that made that model pretty useful for some of the key stakeholders. It was easy to maintain and backfill, as I mentioned earlier, when new requests came in, or when a case happened that, oh, something failed, or we don't have this source for next few hours, the process could easily handle that. It can grab the data whenever it is available and update in Kudu store. Independent of any delay in the source processing, if one source failed, or if you didn't get a data for one single provider from that specific database, it can still handle that. Whenever the information is ready, it will update in that table. Less joins. As I mentioned earlier, that those 3 facts, it could have been a different models, it could have been a different tables, but with this one big fat table, all the metrics from those 3 functional areas were grouped into one table. No need to join 3 tables. You get all your metrics from one table. Now let's go over to a short demo that how you can leverage Spark SQL to analyze the data. I got the public data set that I can use. I can't use like any production ready data from my company. So I'm using a data set from University of California, Irvine. They provided the intrusions of military network simulation, and I'm using that data set. And we'll see that how I can load that data. So just before the start of this session, I connected to a Databricks. I had my commands ready in a notebook. I reran all those commands just to show you that how it worked. I can rerun now as well, but it might take a few seconds, but it might delay it may consume more time. So I'll just go over that how I did that. The first few lines will get the data from this UCI website. It will move the file on Databricks Cloud, and these are the number of records. And if you see, I ran it at 108 today. 2.1 million records in this file. Then what I did was I read that file, and this is the RDD that Spark has created. And I printed the first 5 rows from that RDD, from that text file. This is how the data look like in that CSV file. Then I created a SQL context. To run a SQL query or relational operations, I need to create that SQL context so that I can use that. I'm using Spark 1.6. Currently, like Spark is at 3, and there is a beta version as well. But for the simplicity, I'm using Spark 1.6. So after creating the Spark context, what I did was I splitted all rows by comma. I replaced a new line with a comma, so you can see each line, and I have created a list of all those rows. Then I applied the schema. As I knew that which field is at which position, it may be possible that if I provide a JSON schema, I can apply that schema on text file as well. But for this purpose, I hard-coded that schema element, and I applied that schema on top of this data file. I printed the schema, and now you can see that it's no longer a string. Some of there are long data type strings, and I think only long and strings. Then, if you remember, this is the same query that I showed in the slide, that you can perform group by and aggregation on data frame, and you will see these results on top of that file that we read. At the same time, you can run the different kind of query, and that will return the same result set. This is the same query that we had in that PowerPoint, and if you remember, like these numbers are the same. 602, 065, 20354, it returns the same number. Then I did some complex queries as well, like subqueries and different different queries by protocol type, and mean duration as well. And this is how I got the total number of intrusions by service and attack type. Now, what I did was I wanted to pivot this data. Like that's what sometimes we do to display this information to end users. So now I want to use I want to see the total intrusions by attack type and service in a pivoted table. So now this is what I performed on that data frame, and this is what I got. Like for each service, all this type attack type are shown as the columns now, and all the numbers you can see it here. This is a brief a demo on Spark SQL. I created a Databricks notebook, and I also provided a link of this notebook in my presentation that you will get later. I'll also share it on the application that we are using for scheduling and agenda. And yeah, that is it. Any questions? So the application, I just wanted to show that how you can use Spark SQL to analyze data from raw format. You can, yeah. So it also has the source data and how like different queries that you can perform on that source data to perform your analysis. Thank you everyone for listening to me.
Small token of appreciation.
Oh, thank you very much. Thank you.
What do you use to pull in the source data from the source systems into the flat file?
So what I did was most of our data were in SQL Server databases, and there were like tons of different databases.